putting together everything we know about sums, sum formulas, Riemann sums, and the area under a curve, I want to actually find the area under f of x equals x squared plus 1 on the interval from 0 to 4. To do that, we're going to follow these 3 steps. First, we're going to find a Riemann sum using subintervals of equal width and right-handed endpoints. After we have that sum written down, we're going to use all the things we know about summation rules and formulas to rewrite that Riemann sum as a formula or a function on the variable n. And that way I'd have a formula written down with only an n in it, that if you told me a number of subintervals, I could respond and say this would be the approximated area. And then we're going to take a limit as n approaches infinity to find the actual area. So let's start. Let's find that Riemann sum. So I know my Riemann sum will have a format as a sum from k equals 1 to n of an f of some point, and we're going to use right-hand endpoints, times the delta x. Well, we know what delta x is. Delta x is b minus a all over n, so delta x will be 4 over n, right? This formula would always give me the width if I told you a value for n. My right-handed endpoints, that's always a plus k times delta x, so that's 0 plus k times 4 over n, which is just 4k over n. So now I know what's going on the inside of my function, and I know what delta x is, I can begin to think about my Riemann sum. All right, and now I need to think about what the function does. I need to plug 4k over n in for x. All right, well, this is the function that squares what I plug in. So I have 4k all over n squared plus 1 times delta x, which is still 4 over n. So this is the sum I need to work on. So I'm going to work on that on another board. So I have the sum from 1 to n of 4k over n squared plus 1 times 4 over n. So let's simplify what's on the inside of my summation. So I'll go and square this. That's going to be 16k squared over n squared plus 1, still all times 4 over n. Now what I think I'll do is distribute the 4 over n. So I have 64 times k squared, and now over n cubed, plus 4 over n. All right, well, now I think I see where I can use my rules for the summation. I have the addition, I have addition here on the kth term formula, so I can rewrite this as 2 separate sums. Rewrite things just slightly. All right, so now I have 2 separate sums. I think I'll just go on and do one other thing on this first one, because I have 64 over n cubed. Well, n's just a number. It's the stopping point. It's a number of rectangles. So 64 over n cubed is a constant. In this sum, well, I'm adding 4 over n to itself n times. That's n times 4 over n. That's that constant rule of the sum. So that's just a plus 4 there on the end. And then I have 64 over n cubed times the sum of the first n perfect squares. And I know a formula for that. I can replace that with n times n plus 1 times 2n plus 1 all over 6, and still plus 4 that I had to erase to fit all that in. And so I've worked with my Riemann sum, which I was asked to write down in question number 1, which honestly I had accomplished here, right? That's my Riemann sum. I've really satisfied that. And here I've done enough algebra to have a formula on n. Well, that satisfies number 2, and all I need to do now to find the area is take a limit as n approaches infinity. So finally, the exact area under that curve should be the limit as n approaches infinity of this. 64 over n cubed times n times 2, n times n plus 1 times 2n plus 1 all over 6 plus 4. Now, the only variable here is n. I look at this and this is a rational function on the variable n, right? I can go on and do part of it, the limit as n approaches infinity, of this plus 4 part will just be, well, 4. So now I just need to think about taking the limit of this first part. And I could multiply everything out, right, and get a polynomial. But I'm real lazy and I want to do as much mentally as I can here. And if I were to multiply everything out on the top, I know the highest power of n I would see would be n cubed. Right? If n times 2n would be 2n cubed times 64, the degree on top would be 3. But what I'm really thinking about is that the highest term on top when I multiply it all out would be 128n cubed, right? Because I need to know the highest degree, because I know that if I know the degree of the top and the bottom in a rational function, I'll know how to take this limit. On the bottom, again, the degree is 3, and that's 6n cubed. And I know that when a rational function has the same degree on the top and the same degree on the bottom, there's a horizontal asymptote at the quotient of the two leading coefficients. So as n goes to infinity, I'm going to get 128 over 6. So my actual area should be 128 over 6 plus 4, which, when I reduce it, is 76 over 3. I'm going to check that very quickly in my handy-dandy TI-83. 128 over 6 plus 4 is 25.33, and of course it is 76 thirds. We have found the exact area highlighted in blue here. Now, something really cool. Remember that plus 4 we got on the end, right? It's a 128 over 6 plus 4. I actually see the plus 4. There's a rectangle right here that's 1 by 4. When we shifted this parabola up, we created an area of a plus 4 on it. So I literally see that in my solution. And I don't know, I enjoy that about that picture. I have 2 more examples of finding areas and evaluating Riemann sums.